let yourself settle in for a moment. Find a comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow, deep breath, feeling the air fill your lungs completely, and as you exhale, let any tension dissolve away like morning mist beneath the warming sun. Tonight, we're embarking on a journey through one of humanity's most audacious dreams, but this requires nothing from you except the willingness to drift along with the story, letting it carry you wherever it may lead. We're going to explore something that has captivated imaginations for generations, a dream that seems to defy the very laws that govern our universe. But don't worry about understanding every detail or remembering every equation. Let the words wash over you like gentle waves, painting pictures in your mind of spacecraft gliding between the stars, of distant worlds suddenly within reach, and of a future where the cosmos itself becomes humanity's home. This is a story about breaking barriers, about scientists who dared to ask whether the impossible might, just maybe, be possible after all. So, breathe deeply, relax completely, and let's drift together into a tale of faster-than-light travel, where the boundaries of reality blur with the dreams of tomorrow. The dream of faster-than-light travel. Since the first humans looked up at the night sky and saw those countless points of light scattered across the darkness, we have wondered what lies beyond our world. Those ancient stargazers had no idea of the true scale of what they were seeing. They didn't know that each of those tiny lights was a sun, perhaps surrounded by its own family of planets. They didn't know that the faint smudge of the Milky Way stretching across the heavens was actually our home galaxy, a collection of hundreds of billions of stars wheeling through the void. And they certainly didn't know that beyond our galaxy lay trillions more, each containing their own multitudes of stars and worlds, stretching outward in every direction to distances that would make even their grandest mythologies seem small. But they understood something fundamental that still drives us today. They understood that urge to explore, that deep human need to see what lies beyond the horizon. For most of human history, that horizon was defined by how far we could walk, or how far a horse could carry us, or how far a sailing ship could venture across unknown seas. With each technological advancement, we pushed that horizon farther back. The invention of the steam engine shrank the world. The airplane made continents neighbors. The rocket took us off our planet entirely. On July 20th, 1969, humans stood on another world for the first time. Neil Armstrong and Buzz Aldrin planted their boots in the gray dust of the moon, and for a brief, shining moment, it seemed like the entire solar system would soon be within our grasp. Mars would be next, then the outer planets, then perhaps even the Oort cloud at the edge of our solar system, where billions of comets orbit in the darkness. The future of space exploration seemed limitless. But then reality set in, as it so often does. The moon is our closest celestial neighbor, and reaching it required 3 days of travel aboard a spacecraft moving at roughly 25,000 miles per hour. That's more than 32 times the speed of sound, fast enough to circle the Earth in about an hour and a half. Yet even at that tremendous velocity, reaching the planets of our solar system requires months or years of travel. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object ever created. It has been traveling for nearly 50 years now, moving at about 38,000 miles per hour relative to the Sun, and it has barely begun to leave our solar system. It won't reach the distance of the nearest star for another 73,000 years, 73,000 years. Let that sink in for a moment. When Voyager 1 finally reaches that distance, Earth will be unrecognizable. Entire civilizations will have risen and fallen. Languages we speak today will be long extinct, replaced by tongues we cannot imagine. The very map of the stars will have shifted as they drift through the galaxy. And Voyager 1 won't even actually reach that nearest star. It's heading in a completely different direction. It will simply pass through the same distance that separates us from Alpha Centauri, our closest stellar neighbor. Alpha Centauri is actually a system of 3 stars orbiting each other, located approximately 4.37 light-years from Earth. A light-year, as you probably know, is the distance light travels in 1 year. Light moves at 186,282 miles every single second. In 1 year, it covers nearly 6 trillion miles. And Alpha Centauri lies 4.37 times that distance away. To put this in perspective, imagine you could somehow shrink the sun down to the size of a basketball. On this scale, Earth would be a tiny peppercorn orbiting about 26 feet away. Jupiter would be a small cherry orbiting about 134 feet from the basketball sun. Pluto, at its average distance, would be about 990 feet away, roughly 3 football fields. And on this same scale, where the sun is a basketball and the solar system fits within about 5 city blocks, Alpha Centauri would be another basketball sitting nearly 3,700 miles away. That's roughly the distance from New York City to London. This is the fundamental challenge that has constrained all dreams of interstellar travel since humanity first understood the true scale of the cosmos. Space isn't just big. It's vast beyond comprehension. The distances between stars are so immense that our conventional understanding of travel becomes meaningless. You can't simply build a faster rocket and hope to reach the stars in any reasonable time frame. Even if we could somehow build a spacecraft capable of traveling at 10% the speed of light, about 18,600 miles per second, it would still take 43 years to reach Alpha Centauri. The crew would grow old and die on the journey, and 10% light speed is unimaginably fast by current standards. No human-built spacecraft has ever exceeded a fraction of a percent of light speed. For decades, this seemed to be the end of the story. The laws of physics, as understood by Albert Einstein and confirmed by countless experiments, appeared to place an absolute limit on how fast anything could travel. Nothing with mass, Einstein showed, could reach the speed of light, let alone exceed it. This wasn't just an engineering challenge or a limitation of our current technology. It was written into the fundamental structure of the universe itself. And yet, humanity has never been very good at accepting limitations. Throughout history, we've been told that certain things were impossible, only to eventually figure out how to do them anyway. We were told humans couldn't fly. We were told breaking the sound barrier would destroy an aircraft. We were told reaching the moon was a fantasy best left to the pages of science fiction. Each time, we proved the naysayers wrong. So, perhaps it's not surprising that even as physicists were explaining why faster-than-light travel violated the laws of nature, other scientists were asking a different question. Not whether we could break those laws, but whether we could find a loophole in them. Whether there might be a way to achieve the practical effect of faster-than-light travel without technically violating Einstein's speed limit. Whether the universe might have left open a door, hidden in the mathematics of spacetime itself, that would allow us to slip between the stars after all. The seed of this idea was planted by science fiction, as so many great scientific advances have been. Writers like H.G. Wells, Isaac Asimov, and Arthur C. Clarke imagined futures in which humanity spread across the galaxy, visiting alien worlds and encountering strange new civilizations. But it was Gene Roddenberry's television series, Star Trek, which first aired in 1966, that gave us perhaps the most iconic fictional solution to the light-speed barrier. The Starship Enterprise didn't laboriously accelerate to near-light speeds and coast between the stars. Instead, Captain Kirk simply ordered his engineer to engage the warp drive, and the ship would vanish in a streak of light, arriving at distant star systems in a matter of days or hours. For years, the warp drive remained purely fictional, a narrative device that allowed storytellers to move their characters around a galaxy-spanning setting without boring their audiences with multi-decade voyages. But in 1994, something remarkable happened. A young graduate student in Wales, working on his doctorate in physics, decided to see if there might be any way to make the warp drive real. Understanding the light-speed barrier. To understand why Miguel Alcubierre's 1994 paper was so revolutionary, we first need to understand why the speed of light presented such an insurmountable barrier in the first place. This requires us to delve into one of the most profound and counterintuitive theories in all of physics, Albert Einstein's special theory of relativity, published in 1905 when Einstein was just 26 years old and working as a clerk in the Swiss Patent Office. Before Einstein, physicists thought they understood motion pretty well. If you were standing on a train platform and a train passed by at 50 miles per hour, and someone on that train threw a ball forward at 20 miles per hour, you would see the ball moving at 70 miles per hour, 50 from the train plus 20 from the throw. Simple addition. This seems obvious, intuitive, and in line with our everyday experience. And for slow-moving objects, it's essentially correct. But Einstein realized something profound. Light doesn't behave this way. If you're standing still and measure the speed of a beam of light, you'll find it travels at exactly 186,282 miles per second, or, as physicists usually write it, about 300 million meters per second. Now, imagine you get in a spaceship and accelerate to half the speed of light, then measure that same beam of light. Common sense would suggest you should measure it going at one point 5 times the speed of light, since you're moving toward it. But you don't. You measure it going at exactly the same speed as before, 300 million meters per second. This isn't just strange. It seems impossible. How can the speed of light be the same for everyone, regardless of how fast they're moving? Einstein realized that for this to be true, something else had to give. What gives is our intuitive understanding of space and time. In Einstein's relativity, space and time aren't separate, independent things. They're woven together into a single entity called spacetime, a four-dimensional fabric that can stretch and warp. And, critically, the way spacetime behaves depends on how fast you're moving through it. As you move faster and faster, time for you slows down relative to someone who's standing still, and distances in your direction of motion contract. These aren't optical illusions or measurement errors. They're real, physical changes in the structure of spacetime itself. The mathematics of special relativity are encoded in something called the Lorentz factor, usually represented by the Greek letter gamma. This factor depends on your velocity. At everyday speeds, gamma is essentially equal to 1, meaning relativistic effects are negligible. You can drive your car at 70 miles per hour without worrying about time dilation or length contraction. But, as your velocity approaches the speed of light, gamma grows larger and larger, approaching infinity as you get closer and closer to light speed. This has profound implications for anyone trying to reach light speed. As you accelerate, your mass, or more precisely, your inertial resistance to further acceleration, effectively increases by the Lorentz factor. Double your speed, and it becomes not twice as hard to accelerate further, but exponentially harder. By the time you reach 90% of light speed, you've gained so much effective inertial mass that accelerating by even 1 additional mile per hour requires enormous amounts of energy. And if you somehow reached light speed, the Lorentz factor would become infinite. Your effective mass would be infinite. The energy required to go even the tiniest bit faster would be infinite. And infinity isn't just a really big number. It's a mathematical impossibility, a sign that the theory is telling you something fundamental. You simply cannot get there from here. This is often described by saying that nothing with mass can travel at or faster than the speed of light. But it's more subtle than that. Photons, the particles of light, have no mass at all, and they travel at light speed. In fact, they can't travel at any other speed. If you could somehow slow a photon down, which you can't in a vacuum, it would cease to be a photon. Light speed isn't really about light at all. It's about the fundamental structure of space-time, the maximum rate at which cause can connect to effect, the cosmic speed limit built into the fabric of reality itself. This speed limit isn't just a theoretical nicety. It's been confirmed countless times in particle accelerators around the world. When physicists accelerate electrons or protons to speeds approaching light speed, they find that the particles behave exactly as Einstein predicted. As the particles go faster, they become harder and harder to accelerate further. At the Large Hadron Collider on the border between France and Switzerland, protons are accelerated to 99.9999991% of the speed of light. Even at this incredible velocity, just a tiny fraction short of the light speed barrier, the protons never quite reach it, no matter how much more energy is pumped into them. There's another way to think about the light speed barrier that might be more intuitive. According to relativity, everything in the universe is always moving through space-time at exactly the speed of light. Yes, even you, sitting still right now. But you're not moving through space. You're moving through time. Every second that passes, you move 1 second into the future. That's movement through the time dimension of space-time. When you start moving through space, you're essentially tilting your path through space-time, directing some of your motion away from the time direction and into a space direction. The faster you move through space, the less you move through time. This is time dilation. If you were on a spacecraft traveling at 99% of the speed of light, time would pass about 7 times slower for you than for someone at rest. Your watch would tick normally from your perspective, but if you looked back at Earth, you'd see everything happening in fast forward. The key insight is that you're always moving through space-time at exactly light speed. You can trade motion through time for motion through space, but you can never exceed the total. To move through space at the speed of light, you'd have to stop moving through time entirely. Time would freeze for you, and to go faster than light through space would require moving backward through time, which leads to all sorts of paradoxes and causality violations. It's not just physically impossible, it's logically impossible. For most of the 20th century, this seemed to be the final word on interstellar travel. We could build faster rockets, develop better propulsion systems, perhaps even achieve a small percentage of light speed, given enough engineering ingenuity and resources. But the stars would always remain heartbreakingly out of reach. Even our nearest neighbors would require voyages lasting decades at minimum, and the vast majority of the galaxy would be forever beyond human reach. And yet, as physicists continued to explore the implications of Einstein's theories, both special relativity and its more complex cousin general relativity, which describes how mass and energy warp spacetime to create what we experience as gravity, they began to realize something intriguing. While special relativity places an absolute limit on how fast you can move through space, it says nothing about how fast space itself can move. And that distinction, subtle though it may seem, opened up an extraordinary possibility. The Alcubierre Drive, a theoretical breakthrough. In 1994, Miguel Alcubierre was a graduate student at the University of Cardiff in Wales, working on his doctorate in physics and specializing in something called numerical relativity, the art of using computers to solve Einstein's fiendishly complex equations, describing how spacetime curves and warps. Like many graduate students, Alcubierre needed a break from his research every now and then, and he'd found his escape in Friday night gatherings with friends to watch Star Trek: The Next Generation. Alcubierre had grown up in Mexico City, son of a civil engineer who fostered in his son an appreciation for how mathematics and physics described the real world. As a student, Alcubierre excelled at both mathematics and physics, eventually heading to graduate school in Wales to study under some of the world's leading experts in general relativity. But even as he delved deeper into Einstein's equations, part of his mind remained captured by the science fiction he'd loved since childhood. One Friday evening, as Captain Picard ordered the Enterprise to engage its warp drive and the starship streaked away at faster-than-light speeds, Alcubierre found himself wondering about something. Not whether warp drive was possible. He knew from his physics training that moving through space faster than light was forbidden. But he wondered whether Einstein's equations might allow something that achieved the same practical effect without technically violating the light speed limit. The key insight came from general relativity's description of how spacetime can be curved and distorted by the presence of mass and energy. We experience this curvature as gravity. Earth's mass creates a depression in spacetime, like a bowling ball placed on a rubber sheet. This curvature causes objects to roll toward Earth, which we interpret as gravitational attraction. The more massive an object, the more it warps spacetime, and the stronger its gravity. But general relativity allows for more exotic geometries than simple gravitational wells. It allows for spacetime to be stretched or compressed in various ways, creating regions where the distance between 2 points can be made shorter or longer. And, critically, while special relativity limits how fast you can move through space, it places no such limit on how fast space itself can expand or contract. We see this on cosmic scales. The universe itself is expanding, with distant galaxies receding from us as the space between us and them grows. The most distant galaxies we can observe are receding from us at velocities exceeding the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding, carrying the galaxies along with it. Alcubierre realized that this same principle might be applied on a smaller scale. What if you could create a bubble of spacetime that contracted the space in front of a spacecraft while expanding the space behind it? The spacecraft wouldn't be moving through space at all. It would be sitting still within its own little pocket of flat spacetime, while that pocket was carried forward by the expansion and contraction of space around it. He sat down with paper and pencil as physicists often do, and began working through the mathematics. Over the next few hours, he constructed what would become known as the Alcubierre metric, a mathematical description of a particular configuration of space-time that could, in principle, propel a spacecraft at any speed, including speeds much faster than light, without the spacecraft itself ever accelerating or moving through its local space. The geometry Alcubierre described can be visualized, though imperfectly, like this. Imagine space-time as a vast rubber sheet. Your spacecraft sits in a small region where the sheet is flat and undistorted. Now imagine that the sheet bunches up and compresses in front of the spacecraft, making the distance to distant points shorter, while behind the spacecraft, the sheet stretches and expands, making distances longer. The spacecraft remains in its flat region, like a surfer riding a wave. The wave moves forward, compressing space ahead and expanding space behind, carrying the flat region and its contained spacecraft along with it. From the perspective of someone on the spacecraft, nothing unusual would be happening. They'd be in flat space-time, experiencing no acceleration, no strange forces. Time would pass normally. They could walk around, eat a sandwich, read a book, just as if they were sitting still on Earth. But from the perspective of someone watching from outside, the spacecraft would appear to be moving, potentially at many times the speed of light, as it rode its wave through space. This wasn't just wishful thinking or science fiction dressed up in mathematical clothing. Alcubierre had found a genuine solution to Einstein's field equations, the fundamental equations of general relativity. His metric described a geometrically consistent configuration of space-time that satisfied all of Einstein's requirements. It was, by the strict definition of the term, physically possible within the framework of general relativity. Alcubierre published his paper in the journal Classical and Quantum Gravity with the deliberately provocative title, The Warp Drive, Hyperfast, Travel Within General Relativity. The response from the physics community was a mixture of fascination and skepticism. Yes, the mathematics checked out. Yes, it was technically a solution to Einstein's equations. But there was a massive problem, quite literally. To create the warped spacetime geometry that Alcubierre had described, you would need matter and energy with some very unusual properties. Specifically, you would need what physicists call exotic matter, matter with negative energy density, and lots of it. Alcubierre's initial calculations suggested you would need the equivalent of the entire mass of Jupiter, but with negative sign, to create a warp bubble just a few meters across. Negative energy is one of those concepts that sounds like pure science fiction, but actually has some basis in quantum physics. In the quantum realm, empty space isn't truly empty. It's filled with quantum fields that constantly fluctuate, creating temporary pairs of particles and antiparticles that pop into existence and annihilate each other in tiny fractions of a second. Under certain very specific circumstances, it's possible to create regions where the quantum field has less energy than the vacuum, effectively negative energy. The most famous example is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally verified in the following decades. If you place two uncharged metal plates very close together in a vacuum, they'll experience a tiny attractive force pushing them together. This happens because the quantum fields between the plates are restricted in the wavelengths they can have, while outside the plates all wavelengths are possible. The energy density between the plates becomes slightly less than the energy density outside, creating a negative energy region that pushes the plates together. The Casimir effect proves that negative energy can exist, at least in principle. But the amounts involved are incredibly tiny, and they exist only in microscopic gaps between plates. Scaling this up to create enough negative energy to warp spacetime around a spacecraft would require technologies and capabilities far beyond anything we can currently imagine. Moreover, Alcubierre's calculations showed that the exotic matter wouldn't just be needed in large quantities. It would need to be arranged in a very specific configuration, forming a toroidal ring, like a donut, around the equator of the warp bubble. The negative energy density would need to be precisely calibrated, stronger in some regions and weaker in others, to create the exact spacetime geometry needed for the warp drive to function. Getting any of these details wrong would mean the bubble wouldn't form, or it would form but wouldn't move, or it would move but tear itself apart. There were other problems too. Some physicists pointed out that the warp drive would probably accumulate dangerous particles and radiation on its leading edge, creating a sort of cosmic bow wave that would be catastrophically released when the warp bubble deactivated, potentially sterilizing anything in front of it. Others noted that travelers inside the bubble would be causally disconnected from the universe outside, unable to steer or stop the bubble once it was in motion. And still others raised concerns about causality violations and time travel paradoxes. For all these reasons, most physicists treated the Alcubierre Drive as an interesting mathematical curiosity, a provocative demonstration that Einstein's equations allowed for surprising possibilities, but not as a realistic blueprint for future technology. Alcubierre himself was careful to emphasize that while his metric was consistent with general relativity, actually building such a drive would face enormous, perhaps insurmountable, challenges. But the paper had achieved something important. It had shown that faster-than-light travel wasn't necessarily forbidden by the laws of physics, as we understood them. It was just really, really hard. And in science, there's a big difference between impossible in principle and merely impossible in practice. The first is forever. The second is a challenge. Recent developments and new research, for more than 15 years after Alcubierre published his paper, the warp drive remained a fascinating but purely theoretical concept. Studied occasionally by physicists with time on their hands, but considered far too impractical for serious research funding or engineering efforts. The exotic matter problem seemed insurmountable, and even if negative energy could somehow be generated and controlled, the sheer amount needed made the whole enterprise look hopeless. But then, slowly, things began to change. New research started chipping away at the problems, finding ways to reduce the requirements, eliminate some of the deal-breaking obstacles, and make the warp drive look, if not exactly feasible, at least slightly less impossible than it had seemed before. One of the key figures in this revival of warp drive research was Harold "Sonny" White, a NASA physicist and mechanical engineer who had fallen in love with the concept of faster-than-light travel after encountering Alcubierre's paper as a graduate student. In 2011, while working at NASA's Johnson Space Center, White published a paper titled Warp Field Mechanics 101 that proposed a modification to Alcubierre's original design. White's key insight was that the amount of exotic matter needed depended crucially on the thickness of the warp bubble's wall. Alcubierre's original design had assumed a very thin wall, which required extremely high energy densities to create the necessary spacetime curvature. But White showed, through detailed calculations, that if you allowed the wall to be thicker, spreading the exotic matter out over a larger volume, the peak energy density could be dramatically reduced. Think of it like this. If you want to make a depression in sand, you can either press down hard with your finger, creating a small, deep hole, or you can press down gently with your whole hand, creating a wider, shallower depression. Either way, you're displacing the same amount of sand, but the force per unit area is very different. White's modification was similar. By thickening the bubble wall, the same amount of spacetime curvature could be achieved with much lower energy densities. White's calculations suggested that with an optimally configured warp bubble, the total negative energy requirement might be reduced from something like the mass of Jupiter, down to something more like the mass of the Voyager spacecraft, roughly 733 kilograms. That's still a staggering amount of negative energy, far beyond anything we can currently create, but it's millions of times less than what Alcubierre's original design required. The difference between needing an entire planet's worth of exotic matter and needing less than a ton of it is the difference between absolutely impossible and merely impossible with current technology. White went further, suggesting ways that the energy requirements might be reduced even more. If the intensity of the warp field could be oscillated over time, pulsing on and off in a carefully controlled rhythm, the average energy requirement might drop still further. And if the warp bubble could be shaped differently, perhaps as a toroid with the spacecraft nestled in the center, rather than a sphere around the spacecraft, additional energy savings might be possible. These weren't just mathematical games. White and his colleagues at NASA set up an experiment called the White-Jude Warp Field Interferometer, a device designed to detect extremely small distortions in spacetime. The idea was that if they could create even a microscopic warp field effect in the laboratory, it would prove the concept was real, even if scaling it up to useful sizes remained a distant dream. The interferometer used lasers and sensitive optical equipment to look for tiny changes in the speed of light that might indicate spacetime was being warped. In 2013, White and his team reported that they had detected an anomalous signal in their interferometer that might, possibly, be evidence of a tiny warp field effect. The scientific community remained deeply skeptical, noting that the signal was extremely small and could easily be explained by experimental artifacts or errors. But the work generated significant media attention and renewed interest in warp drive research. Around the same time, other physicists were exploring the fundamental question of whether a warp drive necessarily required exotic matter at all. In 2021, two physicists, Alexei Bobrick and Gianni Martire, published a paper titled Introducing Physical Warp Drives that took a fresh approach to the problem. Instead of starting with Alcubierre's specific design and trying to find ways to make it work, they asked a more general question. What kinds of warp drive geometries are consistent with general relativity, and could any of them be created using only positive energy? Bobrick and Martire showed that yes, certain warp drive configurations could be constructed using only positive energy, avoiding the exotic matter problem entirely. The catch was that these warp drives could only move at subluminal speeds, slower than light. They weren't the faster-than-light warp drives of science fiction, but they were warp drives nonetheless, proving that the concept of warping spacetime for propulsion wasn't inherently tied to exotic matter. More importantly, their work provided a general framework for understanding what makes a warp drive possible. They showed that a warp drive is essentially a shell of material surrounding a region of flat spacetime, with the shell creating a gravitational field that pushes on the flat region, propelling it forward. The shell needs to be massive enough to create a significant gravitational field, which is why even their subliminal warp drive would require several times the mass of Jupiter to move a spacecraft just a few meters across. But in principle, it could work using only ordinary matter and energy. Then came perhaps the most exciting development in warp drive physics since Alcubierre's original paper. In March of 2021, a physicist named Erich Lentz at the University of Göttingen in Germany published a paper titled Breaking the Warp Barrier: Hyper-Fast Solitons in Einstein-Maxwell Plasma Theory. Lentz had been inspired by the Star Trek series he'd watched as a child, and during the COVID-19 pandemic lockdown, he found himself with time to revisit the warp drive problem. Lentz took a completely different approach from Alcubierre. Instead of creating a warp bubble through the expansion and contraction of space, he explored configurations of spacetime organized into structures called solitons. A soliton is a self-reinforcing wave that maintains its shape as it propagates, like a tsunami rolling across the ocean. In the context of spacetime, a soliton would be a stable, localized distortion that could carry a spacecraft along with it. The breakthrough came when Lentz examined a particular class of solitons that nobody had studied before. Ones where the mathematical relationships between different components of the spacetime metric obeyed what's called a hyperbolic relation. When he worked through the mathematics, he found something astonishing. These solitons could move at faster-than-light speeds, just like Alcubierre's warp bubble. But unlike Alcubierre's design, they could be created using only positive energy. No exotic matter required. This was a genuine game-changer. For the first time, someone had found a mathematically consistent way to achieve faster-than-light travel within general relativity using only conventional physics, without invoking exotic matter or negative energy or any other speculative physics that might not exist in our universe. To be clear, Lentz's solution wasn't easy or practical. The energy requirements were still enormous. To create a soliton warp bubble just 100 meters in radius, traveling at the speed of light, would require energy equivalent to hundreds of times the mass of Jupiter. That's still far beyond any conceivable technology. But Lentz pointed out that earlier, research had identified several mechanisms that might reduce energy requirements by as much as 60 orders of magnitude. 1,000,000 trillion times less energy. If even a fraction of those energy savings could be realized, the requirements might drop to something achievable with advanced future technology. The response from the physics community was swift and enthusiastic. Miguel Alcubierre himself called Lentz's work a very important development. Other physicists, while cautious, acknowledged that the mathematics appeared to be correct, and that the work reopened a serious discussion about faster-than-light travel rooted in conventional physics rather than speculation. Building on Lentz's work, other researchers began exploring variations and improvements. Lavinia Heisenberg at the Swiss Federal Institute of Technology Zurich and her student Sean Fell designed their own positive energy warp bubbles that might require as little as 1,000th the mass of our Sun. Still enormous, but orders of magnitude better than earlier estimates. Each incremental improvement made the warp drive look slightly less impossible. In December of 2024, Harold White and his colleagues at a company called Applied Physics published yet another advancement. They proposed a new warp drive design using discrete nacelles, cylindrical structures that generate the warp field, rather than the continuous ring structure of Alcubierre's original design. This modular approach, which somewhat resembles the nacelles of the Starship Enterprise, might be more efficient and easier to control. Alcubierre himself endorsed this new model, lending it significant credibility within the physics community. Most recently, in late 2024 and early 2025, researchers have been exploring how warp drive concepts might connect to other areas of physics. Some have suggested that warp fields might be related to dark energy, the mysterious force causing the universe's expansion to accelerate. Others have proposed laboratory analog experiments using metamaterials or other exotic systems to test warp drive principles at tiny scales. And still others have begun thinking about how we might detect warp drive signatures from other civilizations, turning the search for extraterrestrial intelligence toward looking for distortions in space-time rather than radio signals. All of this recent work hasn't made warp drives practical or even necessarily possible. We're still decades, probably centuries, away from anything like a working prototype, if such a thing ever becomes feasible at all. But the work has accomplished something important. It has moved faster than light travel from the realm of pure fantasy into the realm of extreme engineering challenge. It's no longer a question of whether the laws of physics allow it, but rather a question of whether we'll ever develop the technology to harness those laws to achieve it. The physics of warping space-time. To truly understand what a warp drive would be doing, we need to delve a bit deeper into general relativity and what it means to warp space-time. This is one of Einstein's most profound insights, but it's also one of the most challenging to visualize because it involves things that are completely outside our everyday experience. We live in a world where space seems flat and uniform. If you walk 10 steps north, you cover the same distance as if you walked 10 steps east, or south, or west. Directions might differ, but distances are consistent and predictable. This is Euclidean geometry, the geometry you learned in school, where parallel lines never meet, and the angles of a triangle always add up to 180 degrees. But Einstein showed that this flat geometry is just an approximation that works well when gravity is weak and speeds are slow. In reality, the geometry of space itself, or more precisely space-time, can be curved and distorted by the presence of mass and energy. This curvature is what we experience as gravity. Imagine an ant walking on the surface of a balloon. From the ant's limited perspective, the surface might seem flat. But if the ant walks far enough in what it thinks is a straight line, it will eventually return to where it started, having circumnavigated the balloon. The surface is curved, even though it appears flat at small scales. Space-time works similarly, except instead of being curved in 3 dimensions like a balloon's surface, it's curved in 4 dimensions, including time as one of those dimensions. When you place a massive object like a planet or star in space-time, it creates what physicists call curvature. The more massive the object, the more curvature it creates. We visualize this by imagining space-time as a rubber sheet, and massive objects as heavy balls placed on that sheet. Each ball creates a depression, a well in the fabric. Other objects rolling nearby will naturally curve their paths as they follow the contours of this depression, and we interpret that curved motion as gravitational attraction. This isn't just an analogy. The mathematics of general relativity describes precisely how mass and energy determine the curvature of space-time, and how that curvature in turn determines how objects move through it. Einstein's field equations, published in 1915, are 10 interconnected differential equations that relate the distribution of mass and energy on one side to the geometric properties of spacetime on the other side. Solving these equations for any particular configuration of matter tells you exactly how spacetime curves, and therefore how objects will move. Near Earth, spacetime is only slightly curved. The distortion is subtle enough that Newtonian physics works perfectly well for most purposes. But as you approach more massive objects, or objects where mass is compressed into smaller volumes, the curvature becomes more extreme. Near the Sun, spacetime curves enough that the path of light bends measurably as it passes close by. This bending was famously observed during a solar eclipse in 1919, providing one of the first confirmations of Einstein's theory. Near a black hole, spacetime curves so severely that it creates a one-way boundary, the event horizon, beyond which escape is impossible. At the center, the curvature becomes infinite at a mathematical singularity, a point where our physical theories break down, and new physics is needed to describe what happens. But general relativity allows for more than just the gravitational wells created by massive objects. The field equations permit an enormous variety of different spacetime geometries, including some that behave in very counterintuitive ways. Spacetime can twist, creating something called frame dragging, where rotating massive objects literally drag spacetime around with them. Spacetime can contain ripples that propagate outward as gravitational waves, now detected regularly by observatories like LIGO. And spacetime can expand or contract, creating regions where distances between points change over time, even though the points themselves aren't moving through space. This last property, the ability of spacetime itself to expand or contract, is what makes warp drive possible in principle. We see it on cosmic scales with the expansion of the universe. The space between distant galaxies is growing, causing those galaxies to recede from each other. Importantly, this expansion doesn't have a speed limit. Nearby galaxies recede slowly, distant galaxies recede faster, and the most distant observable galaxies are receding at many times the speed of light. They're not violating relativity because they're not moving through space. Space itself is expanding, carrying them along. The Alcubierre metric and similar warp drive solutions apply this same principle on a local scale. They describe a configuration of space-time where space contracts ahead of a spacecraft and expands behind it, creating a bubble of flat space-time that surfs along the resulting distortion. The spacecraft itself never accelerates. It remains stationary within its bubble of flat space-time, experiencing no forces, while the bubble is propelled forward by the expansion and contraction of space around it. Mathematically, the Alcubierre metric describes spacetime using coordinates where one coordinate measures time and three measure spatial position. The metric itself is a set of equations that tell you how to calculate distances and time intervals between nearby points in this coordinate system. In flat, undistorted spacetime, the metric is simple. The distance between 2 points is just the Pythagorean theorem, the same geometry you learned in school. But in the Alcubierre metric, additional terms appear that couple position and velocity in specific ways. These terms create a flow in spacetime, like a current in a river. Objects in this flow are carried along with it, just as a leaf floating in a river is carried downstream. The clever part of Alcubierre's solution is that he arranged these terms so that the flow is zero inside the bubble where the spacecraft sits, strong and forward-directed just ahead of the bubble, and strong and backward-directed just behind the bubble. This creates a net motion of the bubble through space. The energy required to create this distortion comes from something physicists call the stress energy tensor, a mathematical object that describes how matter and energy are distributed through spacetime. In normal circumstances, the stress energy tensor has positive values: positive energy density, positive pressure, positive momentum flow. These are the properties of all ordinary matter and all known forms of energy. And when you plug positive stress energy into Einstein's field equations, you get the kinds of spacetime curvature we're familiar with: gravitational wells, black holes, gravitational waves. But Einstein's equations also allow, in principle, for negative values in the stress energy tensor: negative energy density, negative pressure, exotic configurations that don't correspond to any known form of matter, but aren't explicitly forbidden by the mathematics. And when you plug certain patterns of negative stress energy into the field equations, you can get warp drive geometries. This is where the exotic matter requirement comes from. To create the Alcubierre warp bubble, you need matter with negative energy density, arranged in a specific pattern around the bubble's perimeter. The negative energy creates a kind of anti-gravity that pushes spacetime apart behind the bubble while simultaneously contracting it ahead of the bubble. Without that negative energy, you can't get the required geometry. The recent work by Lenz and others that claims to avoid exotic matter does so by finding different geometric configurations, different solutions to Einstein's equations that achieve faster-than-light motion through different mechanisms. These solutions still require enormous amounts of positive energy, but positive energy at least exists. We know how to make it. We're made of it. Exotic matter with negative energy, by contrast, might not exist in any useful form anywhere in our universe. One important aspect of warp drive physics that often gets overlooked is what happens at the boundary of the warp bubble. This is where spacetime transitions from the flat geometry inside the bubble to the highly distorted geometry outside. This transition region, the bubble's wall, is where all the interesting physics happens, and it's also where most of the technical challenges arise. The wall needs to be carefully engineered to maintain a stable configuration. Too thin, and the energy densities become impractically high. Too thick, and the bubble becomes inefficient, requiring more energy for the same performance. The wall also needs to be flexible enough to allow the bubble to accelerate, decelerate, and change direction, but stable enough not to collapse or develop instabilities that could destroy it. Some researchers have worried about a runaway feedback effect. As the bubble accelerates, it might collect particles and radiation from the surrounding space, accumulating them at its leading edge. This accumulated matter would itself curve spacetime, potentially reinforcing and amplifying the warp field in unpredictable ways. When the bubble finally stopped, all that accumulated energy would be released in a catastrophic burst, possibly sterilizing everything in front of the spacecraft. Others have pointed out that occupants inside the bubble would be causally disconnected from the outside universe. Light and information from outside the bubble might not be able to penetrate the bubble's wall. This means you couldn't see where you were going, couldn't communicate with the outside world, and couldn't steer or control the bubble from inside. You'd have to set your destination before engaging the warp drive, trust that nothing would get in your way, and hope that your calculations were correct. These aren't just engineering challenges. Some of them might be fundamental limitations of warp drive physics. If you can't send signals from inside the bubble to outside, you might need an automated navigation system on the bubble's exterior, or you might need to drop out of warp periodically to see where you are and make course corrections. If accumulated radiation at the bubble's leading edge is unavoidable, you might need to keep warp journeys short, or develop some way to deflect or dissipate the radiation before it builds to dangerous levels. Engineering challenges and energy requirements. Even if we accept that warp drives are possible in principle, and even if we find a way to create them without exotic matter, the engineering challenges are staggering. Let's talk about numbers, because numbers often clarify just how far we are from turning theory into technology. Alcubierre's original 1994 design required negative energy, equivalent to the entire mass of Jupiter. Jupiter has a mass of about 1.9 times 10 to the 27th power kilograms. That's 1.9 followed by 27 zeros. To put that in perspective, the entire Earth has a mass of about 6 times 10 to the 24th power kilograms. Jupiter is 318 times more massive than Earth. So, Alcubierre was talking about gathering up more than 300 Earths worth of exotic matter and arranging it in a ring around your spacecraft. Obviously, this is impossible. We don't have exotic matter, and even if we did, manipulating planetary masses is far beyond our capabilities. The International Space Station, one of the largest structures ever placed in orbit, has a mass of about 420,000 kilograms. The Saturn V rocket that sent astronauts to the Moon had a total mass at launch of about 2.8 million kilograms. The largest object humanity has ever built and moved, the Bagger 293 bucket wheel excavator in Germany, weighs about 14 million kilograms. Even this enormous machine is 23 orders of magnitude, 10 trillion times, less massive than Alcubierre's energy requirement. Harold White's modifications, published in 2011, brought the requirement down dramatically. By optimizing the bubble's shape and thickness, White calculated that the negative energy requirement could be reduced to about 700 kilograms, equivalent to the Voyager spacecraft. This is still an enormous amount of negative energy, far more than has ever been created in any laboratory, but it's at least within the realm of things that are theoretically conceivable. 700 kilograms is a mass humans can work with. We build machines of that mass routinely. The question becomes, could we ever generate 700 kilograms worth of negative energy? The Casimir effect, which we mentioned earlier, does create negative energy, but in incredibly tiny amounts. The force between two Casimir plates 1 micrometer apart, about 1/100th the width of a human hair, is roughly 1/1000th of a Newton per square meter. For comparison, atmospheric pressure at sea level is about 100,000 newtons per square meter. The Casimir force is vanishingly weak. To generate significant amounts of negative energy through the Casimir effect would require structures of enormous size and precision. Some physicists have speculated about using metamaterials, artificially engineered materials with properties not found in nature, to enhance the Casimir effect by many orders of magnitude. Others have proposed using strong lasers or electromagnetic fields to create regions of negative energy in quantum fields. But these remain purely speculative. Nobody has demonstrated the creation of negative energy at scales even remotely approaching what would be needed for a warp drive. Then there's Lenz's positive energy design from 2021. This avoids the exotic matter problem entirely, but comes with its own enormous energy requirement. Lenz calculated that his warp bubble would require energy equivalent to about 10 to the 30 power kilograms of matter converted to pure energy via Einstein's equation E equals mc squared. That's about 100 times the mass of the Sun. The Sun, our local star, has a mass of about 2 times 10 to the 30 power kilograms. It's been converting mass to energy through nuclear fusion for 4.6 billion years. And in all that time, it has converted about 0.1% of its mass to energy. To power Lenz's warp drive, even for a brief journey, would require converting a significant fraction of the Sun's entire mass to pure energy, and somehow channeling all that energy into creating the precise space-time distortion needed for the warp bubble. To put this in perspective, the most energetic event humanity has ever created was the detonation of the Tsar Bomba, a Soviet thermonuclear weapon tested in 1961. This device, the most powerful explosive ever detonated, released about 210 petajoules of energy, equivalent to about 50 megatons of TNT. It was powerful enough to create a fireball 8 kilometers across, break windows 800 kilometers away, and send a mushroom cloud that reached more than 60 kilometers into the atmosphere. That enormous explosion converted about 1.4 grams of matter to energy. 1.4 grams. About the mass of a small paperclip. And it took the most sophisticated nuclear weapons technology available to achieve even that modest mass energy conversion. To power Lenz's warp drive would require converting kilograms upon kilograms of matter to energy, not over years or decades, but instantaneously, and doing so in a controlled way that creates the precise geometric distortion needed, rather than just exploding destructively. However, Lenz pointed out that there might be ways to reduce these energy requirements dramatically. Previous theoretical work had suggested various mechanisms that could make warp drives more efficient. If the warp field could be made to resonate at particular frequencies, if quantum effects could be harnessed, if the design could take advantage of certain symmetries or conservation laws, the energy requirements might drop by factors of 1,000,000, 1,000,000,000, or even more. One particularly promising avenue involves something called energy-momentum exchange with the quantum vacuum. The vacuum of space isn't truly empty. It's filled with quantum fields that are constantly fluctuating. Under certain circumstances, it might be possible to borrow energy from these fluctuations temporarily, use it to create the warp field, and then pay it back. This wouldn't violate conservation of energy because the borrowing would be temporary, but it might allow the creation of warp fields that would otherwise require impossibly large energy inputs. Another possibility involves using rotating or spinning configurations of matter and energy. The frame dragging effect, where rotating massive objects literally drag spacetime around with them, might be harnessed to reduce the energy needed to create warp geometries. Some physicists have proposed using rapidly rotating cylinders of dense matter, or toroidal rings of circulating energy, to create spacetime distortions that could be the beginning of a warp field. These ideas remain highly speculative, but they illustrate an important point. The energy requirements we can calculate now are based on straightforward applications of our current understanding of physics. As we learn more about quantum gravity, about the nature of spacetime at the smallest scales, about the properties of matter and energy under extreme conditions, we might discover new principles or effects that make warp drives more achievable than our current calculations suggest. There are also enormous engineering challenges that have nothing to do with energy. Suppose you somehow solved the energy problem and could create a warp bubble. How would you control it? The mathematics suggests that once inside a warp bubble, you're causally disconnected from the outside universe. This means signals from inside can't reach outside, and signals from outside can't reach inside. You couldn't steer. You couldn't see where you were going. You couldn't communicate with anyone. You'd be trapped in your own private pocket universe until the warp field dissipated. Some researchers have proposed solutions to this problem. Maybe you could create small controlled variations in the warp field that would allow limited communication or sensing. Maybe you could use pre-programmed external systems that ride on the outside of the bubble to provide navigation and control. Maybe you could periodically drop the warp field, check your position and course, and then re-engage it with corrections. But all of these add complexity and reduce the practical utility of the drive. Then there's the problem of starting and stopping. Creating a warp bubble around a spacecraft requires manipulating space-time in a very specific way. This presumably requires some kind of field generator or exotic matter distributor built into the spacecraft itself. But how do you bootstrap such a system? If the field generators are inside the bubble they're creating, how do they reach outside to shape the surrounding space-time? If they're outside the bubble, how do the occupants control them once the bubble forms? And stopping might be even harder than starting. The mathematics suggests that enormous amounts of energy would be trapped in the warp field structure. Dissipating this energy safely when you want to drop out of warp could be extremely difficult. Some calculations suggest that the energy would be released as a devastating burst of radiation and particles, effectively weaponizing every arrival. Imagine trying to visit a star system if, every time you arrive, you automatically sterilize anything in front of you with a blast of radiation energetic enough to scour planets clean of life. Material science presents its own challenges. Any structure associated with a warp drive would need to withstand enormous stresses. The space-time curvature at the boundary of the warp bubble would be extreme, creating tidal forces that would stretch and compress anything passing through that boundary. The spacecraft itself, sitting in the flat region inside the bubble, might be safe from these forces, but any part of the ship that had to extend into or through the bubble wall would need to be extraordinarily strong. We don't currently have materials that could survive such conditions. The strongest materials we know, things like carbon nanotubes or graphene, have tensile strengths measured in gigapascals, billions of newtons per square meter. But the tidal forces near a warp bubble's boundary might be many orders of magnitude stronger. We'd need materials with properties far beyond anything currently known, or we'd need to engineer the bubble's geometry to minimize these forces, which might conflict with the need to keep the bubble as small and efficient as possible. There's also the question of time. Even if we could solve all the technical challenges, how long would it take to build a warp drive? At a minimum, we'd need to develop technologies that are currently beyond our capabilities in multiple areas simultaneously. We'd need breakthroughs in our understanding of quantum gravity. We'd need revolutionary advances in energy generation and manipulation. We'd need entirely new materials with properties unlike anything in nature. We'd need computational capabilities far beyond our current supercomputers to model and control the complex dynamics of space-time distortion. Each of these is likely a century-scale challenge on its own. Quantum gravity has been pursued by the brightest minds in physics for decades, with only limited success. Fusion energy, which would be trivial compared to the energy manipulation required for a warp drive, has been 30 years away for the past 60 years. Revolutionary materials take decades from discovery to practical application. And While computer capabilities continue to advance, the calculations needed to model warp field dynamics might be beyond even quantum computers. Optimistically, if everything went perfectly and multiple major breakthroughs occurred in rapid succession, we might conceivably have a crude proof-of-concept demonstration of a microscopic warp field by the end of this century. Scaling that up to a usable spacecraft might take another century or two. More realistically, warp drives, if they're possible at all, are probably a technology of the 23rd or 24th century, assuming human civilization survives and continues to advance. Alternative approaches to faster-than-light travel. While warp drives have captured the public imagination and received the most scientific attention, they're not the only theoretical approach to faster-than-light travel. Other ideas, some even more exotic than warp drives, have been proposed over the years. Let's explore a few of them. Perhaps the most famous alternative is the wormhole, also known as an Einstein-Rosen bridge, after the physicists who first described them mathematically in 1935. A wormhole is essentially a tunnel through spacetime, connecting two distant locations. Instead of traveling the long way through normal space, you could enter one end of the wormhole and emerge almost instantly at the other end, potentially light years away. The mathematics of general relativity does allow for wormhole solutions, but like warp drives, these solutions come with severe practical limitations. First, wormholes as Einstein and Nathan Rosen originally described them aren't traversable. They form and collapse so quickly that nothing, not even light, could pass through before the wormhole pinched shut. Making a traversable wormhole, one that stays open long enough for something to pass through, requires exotic matter with negative energy, the same stuff needed for Alcubierre-style warp drives. Second, even if you could create a traversable wormhole, it wouldn't automatically connect to wherever you wanted to go. The two ends of the wormhole, called mouths, would initially be near each other in space. To make the wormhole useful for interstellar travel, you would need to move one mouth to your destination. But moving the mouth requires conventional travel, limited by the speed of light. So, to create a wormhole connection to a star 10 light-years away, you'd first need to spend at least 10 years moving one mouth of the wormhole there using conventional propulsion. This leads to an interesting scenario. A wormhole could be useful for making return trips or establishing a permanent transportation network, but it wouldn't help with the initial exploration of distant stars. You'd still need slower-than-light starships to get the wormhole mouths into position initially. Only after that, infrastructure was built, could you use wormholes for rapid transit. There's also a disturbing possibility that wormholes might enable time travel. If you could move one mouth of a wormhole at high speed and then return it to near the other mouth, relativistic time dilation would cause the two mouths to be at different times. Entering one mouth might let you emerge from the other mouth in the past, creating all sorts of paradoxes. Some physicists argue that the laws of physics might automatically prevent this, perhaps causing the wormhole to collapse or become non-traversable whenever a time loop threatens to form. Another speculative idea involves quantum entanglement, the mysterious connection that can exist between particles no matter how far apart they are. When two particles are entangled, measuring one particle instantly affects the state of the other, even if they're on opposite sides of the galaxy. Einstein famously called this spooky action at a distance, and was deeply uncomfortable with it. Could quantum entanglement be harnessed for faster-than-light communication or travel? Unfortunately, probably not. While the correlation between entangled particles is instantaneous, you can't use it to send information faster than light because the measurement results at each end appear random until you compare them. And comparing them requires sending a signal by conventional means, limited by light speed. Some physicists have speculated about more exotic possibilities. Maybe quantum entanglement could be used to create something called an ER equals EPR bridge, a wormhole connection based on quantum entanglement. This idea, proposed by physicists Juan Maldacena and Leonard Susskind, suggests a deep connection between the geometry of spacetime and the quantum information of entangled particles. But even if this connection is real, it's unclear whether it could be harnessed for practical faster-than-light travel or communication. Then there are hypothetical particles called tachyons, which would travel faster than light naturally. In special relativity, if something traveled faster than light, it would have an imaginary rest mass, meaning its mass squared would be negative. This seems nonsensical, but mathematically it's consistent with the equations. If tachyons exist, they would experience time differently, potentially moving backward through time from our perspective. The problem with tachyons is that there's no evidence they exist, and good theoretical reasons to think they don't. If tachyons existed and could interact with normal matter, they would violate causality, allowing effects to precede their causes and creating logical paradoxes. Most physicists believe that tachyons are mathematical curiosities that don't correspond to anything real in our universe. Some scientists have proposed using shortcuts through higher dimensions. If our universe is actually embedded in a higher dimensional space, the way a two-dimensional sheet of paper exists in our three-dimensional world, then traveling through that higher dimensional space might allow you to take shortcuts between distant points in our universe. This is similar to how an ant walking on the surface of a paper can only travel along the paper's surface, but if you fold the paper, two distant points on the surface might actually be very close through the third dimension. String theory and related frameworks do suggest that extra dimensions beyond our familiar three spatial dimensions and one time dimension might exist. But these extra dimensions, if real, are probably tiny, curled up on scales far smaller than atoms. Accessing them would require energies far beyond anything achievable. And even if we could access higher dimensions, it's not clear we could navigate through them usefully. Perhaps the most practical alternative to faster-than-light travel is to simply accept the speed limit and plan accordingly. Generation ships, enormous spacecraft designed to support populations across multiple generations, could travel to nearby stars at speeds of perhaps 1 to 10% of light speed. The original crew would die of old age during the journey, but their descendants would arrive at the destination, perhaps centuries later. Or we could use suspended animation or cryogenic freezing to keep crews alive during the decades or centuries of travel time. If reliable suspended animation became possible, a journey that took 100 years from Earth's perspective might seem instantaneous to the sleeping crew. They'd go to sleep in Earth orbit and wake up in orbit around a distant star, unaged and ready to explore. Another approach is to not send biological humans at all. We could send robotic probes equipped with artificial intelligence to explore distant stars. These probes wouldn't care how long the journey took. They could hibernate during the transit, activating only when they reached their destinations. And they could send back information at light speed, allowing humans on Earth to learn about distant worlds without physically traveling there. Or, perhaps most radical, we could upload human consciousness into machines or purely digital substrates. If human minds could exist as software running on advanced computers, those minds could travel at light speed as radio signals beamed between stars. The biological bodies would stay home, but consciousness and identity could travel across the galaxy, downloading into new robotic bodies at each destination. All of these alternatives avoid the need for faster-than-light travel, working within the constraints imposed by relativity. They're not as exciting as warp drives or wormholes, but they might be more realistic approaches to becoming an interstellar civilization. Implications for humanity's future. The possibility of faster-than-light travel, however distant that possibility might be, has profound implications for humanity's long-term future. To understand why, we need to think about the challenges facing our species over the coming centuries and millennia, and how access to the stars might address them. Earth is an extraordinary planet, but it's also fragile and finite. We're currently experiencing climate change driven by our own activities, seeing ecosystems collapse under the weight of habitat destruction and pollution, and depleting finite resources at unsustainable rates. While these are problems we've created and therefore problems we can potentially solve, they highlight a fundamental vulnerability. All of human civilization, every person who's ever lived, every achievement, every work of art, every discovery, exists on a single world orbiting a single star. This is an extraordinarily precarious situation. A sufficiently large asteroid impact could devastate or even sterilize Earth. We know from the geological record that such impacts have happened before. 66 million years ago, an asteroid about 10 kilometers across struck what is now the Yucatan Peninsula in Mexico, ending the reign of the dinosaurs and causing the extinction of roughly 3/4 of all species on Earth. Smaller impacts occur more frequently. In 1908, an object probably less than 100 meters across exploded over Tunguska in Siberia, flattening 2,000 square kilometers of forest. If it had struck over a populated area, millions might have died. We're getting better at tracking potentially hazardous asteroids, and we're beginning to develop the capability to deflect them if given sufficient warning. But asteroid impacts aren't the only existential risk. A nearby supernova or gamma ray burst could bathe Earth in deadly radiation. An extreme solar flare could overwhelm our planet's magnetic defenses. And there are risks of our own making, too. Nuclear warfare, engineered pandemics, runaway artificial intelligence, or environmental collapse that makes the planet uninhabitable. The probability of any particular catastrophe occurring in any given year is low. But over centuries and millennia, the cumulative risk becomes significant. As long as humanity is confined to a single planet, we're vulnerable. The solution, many scientists and philosophers argue, is to become a multiplanetary species, establishing permanent settlements on other worlds so that no single catastrophe can end human civilization. Our solar system offers some possibilities. Mars is the most obvious candidate. A planet with a 24-hour day, polar ice caps, and enough resources to theoretically support a self-sufficient colony. But Mars is cold, has no magnetic field to protect against radiation, and has an atmosphere that's less than 1% as dense as Earth's. Living on Mars would mean living in sealed habitats or underground, never breathing the thin Martian air or feeling unfiltered sunlight on your skin. The moons of Jupiter and Saturn offer possibilities too. Europa, orbiting Jupiter, has more water than all of Earth's oceans combined, locked beneath an icy crust. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane. But these are even more hostile environments than Mars, colder and more distant, bathed in deadly radiation from their giant planets. We could build rotating space habitats, enormous cylindrical or toroidal structures that create artificial gravity through rotation. These O'Neill cylinders, named after physicist Gerard K. O'Neill, who popularized the concept in the 1970s, could house thousands or millions of people in Earth-like environments, complete with artificial skies, forests, and lakes. But building them would require enormous resources and industrial capacity, probably requiring extensive mining of asteroids and the moon. All of these approaches would make us a multi-world species, reducing our vulnerability to single-point failures. But they keep us confined to our solar system, still dependent on a single star, still vulnerable to any catastrophe affecting the Sun itself. In about 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, eventually engulfing the inner planets including Earth. Long before that, within the next billion years, the Sun will gradually brighten as it ages, eventually becoming hot enough to boil Earth's oceans and make the planet uninhabitable. 1 billion years sounds like a long time, and it is. It's longer than multicellular life has existed on Earth, but it's also finite. If humanity or our descendants are still around then, they'll need to have moved elsewhere. And even on shorter timescales, remaining confined to a single solar system limits our potential. There are 400 billion stars in the Milky Way, many of them likely surrounded by planets. Some fraction of those planets are probably habitable. By remaining in our solar system, we'd be ignoring 99.9999% of the potential living space available to us. This is where faster-than-light travel changes everything. If we could travel between stars quickly, all of those hundreds of billions of potential homes would become accessible. Humanity could spread throughout the galaxy, establishing colonies on countless worlds. Even if some colonies failed or were destroyed by natural or artificial catastrophes, the species would survive in thousands of other locations. We would become truly resilient against extinction. The social and cultural implications would be equally profound. Human history has been shaped by exploration and contact between different cultures. The Silk Road connected East and West, spreading technologies, religions, and ideas across Asia and Europe. The age of exploration brought Europeans into contact with the Americas, leading to exchanges, some beneficial and some catastrophic, that shaped the modern world. The development of rapid global communication has created an increasingly interconnected global culture. An interstellar civilization would amplify these dynamics immensely. Each colony world would develop its own unique culture, shaped by its environment, its founding population, and the random drift of cultural evolution over generations. Over time, these cultures might diverge so much that they'd be barely recognizable to each other. But with faster-than-light travel, they could remain in contact, trading goods and ideas, learning from each other's successes and failures. The diversity of human experience would expand in ways we can barely imagine. There's also the possibility, perhaps even the likelihood, that we're not alone in the universe. The sheer number of stars and planets makes it seem improbable that Earth is the only world where life arose. If life is common, or even if it's rare but still exists elsewhere, then spreading into the galaxy increases our chances of making contact with other intelligence. Such contact would be one of the most significant events in human history. It would answer the age-old question of whether we're alone. It would provide insights into alternative paths of biological and cultural evolution. It might offer technologies or knowledge we haven't discovered on our own, and it would force us to think about our place in a cosmic community, rather than thinking of ourselves as the lone intelligence in an empty universe. Of course, contact with extraterrestrial intelligence also carries risks. We don't know how other civilizations might react to us, or how we might react to them. Science fiction has explored both utopian scenarios of peaceful cooperation and dystopian scenarios of conflict and conquest. The reality would probably be more complex than either extreme. But faster-than-light travel would at least give us the capability to explore and encounter the universe on our own terms, rather than waiting passively for contact to happen on someone else's schedule. Even beyond the question of extraterrestrial intelligence, the galaxy is full of wonders we'd like to study directly. We've discovered thousands of exoplanets orbiting other stars, and their diversity is astonishing. There are hot Jupiters, giant planets orbiting closer to their stars than Mercury orbits the Sun. There are super-Earths, rocky planets larger than Earth but smaller than Neptune. There are planets orbiting binary star systems, worlds that would have 2 suns in their skies. And there are probably billions of Earth-like planets in the galaxy, worlds where liquid water could exist on the surface and life might have arisen. With current technology, we can study these worlds only at a distance, analyzing the tiny dimming of starlight as a planet passes in front of its star, or measuring the subtle wobble in a star's position caused by an orbiting planet's gravity. These techniques tell us about planetary size, mass, and orbital period. With advanced telescopes, we can even begin to analyze planetary atmospheres, looking for chemical signatures that might indicate life. But there's only so much you can learn from billions of miles away. To really understand these worlds, to know whether they harbor life, to see their landscapes and breathe their air, you need to go there. Faster-than-light travel would make that possible. Instead of being confined to analyzing distant spectra, we could send missions to any interesting planet, studying them directly, searching for life, and perhaps even finding habitable worlds where humanity could establish new homes. The economic implications would be equally staggering. Our solar system contains enormous resources, asteroids rich in metals, moons covered in water ice, gas giants whose atmospheres contain more helium and hydrogen than we could ever use. But other solar systems contain their own resources, perhaps including materials or isotopes rare in our own system. Trade between star systems could create an interstellar economy, with each system specializing in what it produces best and trading for what it needs. Imagine shipments of rare elements mined from the core-rich planets of one system, traded for manufactured goods produced in the orbital factories of another. Imagine information markets, where new technologies and cultural works flow between stars, enriching every civilization they touch. Imagine tourism, with beings from one world visiting others to experience different environments, different cultures, different perspectives. This isn't just idle speculation. Every major expansion of transportation networks in human history has been followed by an explosion of economic activity and cultural exchange. When the Transcontinental Railroad connected the east and west coasts of North America, it transformed the economy of the continent. When commercial aviation made rapid intercontinental travel affordable, It created a global economy where goods and people flow constantly across borders. An interstellar transportation network would do the same thing on a galactic scale. Of course, faster-than-light travel also carries potential dangers. The same technology that would allow us to explore and colonize the galaxy could be used for warfare. Ships capable of crossing light years in days or hours could deliver weapons, or could themselves be used as weapons if crashed into planets at relativistic speeds. A sufficiently advanced warp drive might be able to destabilize stars or even black holes, weaponizing astronomical bodies. And there are philosophical concerns too. Would spreading throughout the galaxy be a good thing for humanity, or would it simply export our problems to a larger stage? Would we bring war, exploitation, and environmental destruction to pristine worlds? Would we repeat the mistakes of colonialism, with powerful civilizations exploiting weaker ones? Or would the vastness of space and the abundance of resources reduce conflict, giving every group room to pursue their own destiny without infringing on others? These are questions we'd need to grapple with long before we actually develop faster-than-light travel. The technology itself is morally neutral. It's a tool, and like any tool, it can be used well or poorly. Ensuring that we use it well would require wisdom, foresight, and careful ethical consideration. But the potential benefits for the long-term survival and flourishing of humanity and our descendants are so enormous that the pursuit seems worthwhile. The path forward and current research. So where are we now, and what would it take to move from theoretical speculation to actual progress toward faster-than-light travel? The current state of research can be characterized as very early-stage theoretical work, with no experimental validation and no clear path to engineering applications, but with a growing community of serious physicists taking the possibility seriously enough to work on it. The first step, already well underway, is continuing to refine the theoretical foundations. Physicists are exploring different warp drive geometries, looking for configurations that might be more efficient or easier to create than Alcubierre's original design. They're studying the stability of warp bubbles, trying to understand whether these structures would be stable over time or would quickly collapse due to small perturbations. They're investigating the effects of quantum mechanics, which Alcubierre's original work ignored, to see whether quantum effects might help or hinder warp drive formation. One particularly active area of research involves numerical simulations. Einstein's field equations are notoriously difficult to solve exactly for all but the simplest configurations. Most real systems require approximate solutions found using powerful computers. Researchers are developing increasingly sophisticated simulations that can model the formation, evolution, and properties of warp bubbles in detail. These simulations help identify potential problems and opportunities that aren't obvious from the mathematical analysis alone. Another important research direction involves looking for laboratory analogs of warp drive physics. While we can't create actual warp drives in laboratories, we might be able to create systems that behave analogously, obeying similar mathematics but in different physical contexts. For example, researchers have studied how sound waves propagate in certain fluid systems, finding configurations where the fluid flow creates acoustic event horizons analogous to black hole event horizons. Similar analog systems might exist for warp drive physics, allowing us to study the relevant phenomena in accessible laboratory settings. There's also growing interest in looking for warp drive signatures in astronomical data. If advanced extraterrestrial civilizations exist, and have developed faster than light travel, their warp drives might create detectable disturbances in spacetime. These disturbances might show up as gravitational wave signals with particular characteristics, or as unusual patterns in the distribution of matter and energy in certain regions of space. The Laser Interferometer Gravitational Wave Observatory, or LIGO, which has been detecting gravitational waves from colliding black holes and neutron stars since 2015, might potentially detect warp drive signals if they exist and if they're strong enough. Several researchers have proposed specific experimental tests that could be performed in the relatively near future. Harold White's White-Jude Warp Field Interferometer, mentioned earlier, is one example. While the initial results were inconclusive and controversial, the basic idea is sound. If we can create even a tiny perturbation in spacetime using available technology, and detect that perturbation reliably, it would prove the principle that artificial spacetime manipulation is possible. Other proposed experiments involve using high-energy lasers or particle beams to create brief, intense concentrations of energy that might momentarily distort spacetime in measurable ways, or using superconducting rings carrying enormous electric currents to generate strong electromagnetic fields that might interact with spacetime. These experiments would be expensive and challenging, requiring equipment and capabilities at the limits of current technology, but they're not fundamentally impossible. If any of these experiments succeeded in detecting even a tiny warp drive effect, it would revolutionize the field. It would transform warp drives from mathematical curiosities into real phenomena that could be studied experimentally. It would open up entirely new research programs aimed at understanding and enhancing the effect. And it would provide justification for much larger investments in warp drive research. But even if we could demonstrate warp drive effects in laboratories, scaling those effects up to useful sizes would be an enormous challenge. The gap between demonstrating a principle in a laboratory and building a working spacecraft is often measured in decades or centuries. Consider nuclear fission. The basic physics was understood in the 1930s, and the first controlled nuclear reaction was achieved in Chicago in 1942. But it took many more years to develop nuclear power plants, and we still struggle with making fusion energy, a related but more complex process, practical for power generation. Or consider heavier-than-air flight. The Wright brothers made their first powered flight in 1903. Less than 12 years later, aircraft were being used as weapons in World War I. Less than 40 years later, jet aircraft were breaking the sound barrier. And less than 70 years later, humans walked on the moon. The progress was astonishingly rapid by historical standards, driven by massive investments during wartime and the Cold War. Warp drive development, if it ever happens, might follow a similar trajectory. An initial laboratory demonstration might be followed by decades of gradually larger experiments, culminating eventually in a prototype capable of moving a spacecraft. But the timeline could easily stretch across centuries rather than decades, especially if progress depends on fundamental breakthroughs in physics that we can't currently anticipate. One challenge is that warp drive research doesn't have obvious spin-off applications that would justify large investments. Nuclear physics led to both weapons and power generation, providing strong incentives for governments and corporations to fund research. Rocket science was driven by both military applications and the space race between the United States and Soviet Union. But warp drives, at least based on our current understanding, don't have intermediate applications. Either you build a working warp drive capable of moving a spacecraft faster than light, or you have nothing useful. This might change if we discover that the same physics underlying warp drives could be applied to other problems. Maybe warp field manipulation could be used for propulsion at slower speeds, making interplanetary travel more efficient. Maybe it could be used for power generation, extracting energy from space-time distortions. Maybe it could enable new types of sensors or communication systems. If warp drive physics turns out to have near-term applications, funding and progress would accelerate. Another factor is the socio-political context. Major technological leaps often require sustained commitment across generations, with societies willing to invest enormous resources in long-term projects whose benefits won't be realized for decades. The cathedral builders of medieval Europe worked on projects that wouldn't be completed in their lifetimes. The Apollo program that landed humans on the moon required a decade of effort and enormous expense, justified by the Cold War competition with the Soviet Union. Would contemporary or future societies be willing to make similar commitments to developing faster-than-light travel? The answer probably depends on whether compelling reasons emerge to make the investment worthwhile. If we discover evidence of habitable planets around nearby stars, the desire to reach them might provide motivation. If we make contact with extraterrestrial intelligence, and they have faster-than-light travel, we might be motivated to match their capabilities. Or if humanity faces existential risks that make spreading beyond our solar system imperative for survival, warp drive development might become a priority. The role of private enterprise might also be important. In recent years, companies like SpaceX, Blue Origin, and others have demonstrated that private companies can achieve goals in space that were previously the exclusive domain of governments. SpaceX has dramatically reduced the cost of launching payloads to orbit and has developed partially reusable rockets that were once thought impractical. If similar innovation and cost reduction could be applied to warp drive research, progress might accelerate beyond what government-funded programs alone could achieve. There's also the possibility that warp drives will turn out to be impossible for reasons we don't yet understand. Our current theories, general relativity and quantum mechanics, are immensely successful at describing the universe, but we know they're incomplete. General relativity doesn't incorporate quantum effects, and quantum mechanics doesn't properly handle gravity. At extreme conditions, like the interior of black holes or the first moments after the Big Bang, both theories break down and new physics is needed. This new physics, whatever it turns out to be, whether it's string theory, loop quantum gravity, or something else entirely, might impose additional constraints that rule out warp drives entirely. Or it might open up new possibilities that make them easier than we currently think. We simply don't know. The only way to find out is to continue researching, continue pushing the boundaries of our understanding, and remain open to surprises. Whatever the ultimate fate of warp drive research, the pursuit itself is valuable. Some of the most important scientific discoveries have come from pursuing ideas that seemed impossible. The laser was once called a solution looking for a problem. But now lasers are everywhere, from medical devices to telecommunications to manufacturing. Nuclear magnetic resonance was a curiosity in atomic physics before it became magnetic resonance imaging, one of the most powerful medical diagnostic tools ever developed. Even if warp drives prove impossible, the research will deepen our understanding of space-time, gravity, and the fundamental nature of reality. It will drive the development of new mathematical techniques, new experimental methods, new technologies. And it will inspire people, especially young people, to pursue careers in science and engineering, drawn by the audacious dream of reaching the stars. Conclusion. As we drift toward the end of our journey tonight, let's take a moment to reflect on how far we've come, both in this story and in humanity's ongoing quest to understand and explore the universe. We started by acknowledging the fundamental barrier imposed by the speed of light, that cosmic speed limit that seems to place the stars forever beyond our reach. We explored how Einstein's relativity established that barrier, weaving space and time together into a unified spacetime where nothing with mass can reach light speed, let alone exceed it. But then we saw how creative thinking revealed potential loopholes in those restrictions. Miguel Alcubierre showed that while we can't move through space faster than light, space itself faces no such limitation. His warp drive concept, riding a wave of contracting and expanding space-time, opened a door that had seemed permanently closed. Yes, the exotic matter requirement seemed insurmountable, but the mathematics worked. Faster-than-light travel wasn't forbidden in principle, just extraordinarily difficult in practice. And then, over the past few years, we've seen renewed energy in the field. Harold White's modifications reduced energy requirements by factors of millions. Eric Lentz found warp drive solutions that don't require exotic matter at all, using only positive energy, even if still in enormous quantities. Other researchers continue to chip away at the problems, finding incremental improvements and new approaches. The goal remains distant, perhaps centuries away, but it's no longer quite as impossible as it once seemed. We've also seen that faster-than-light travel isn't just about satisfying our curiosity or fulfilling the dreams of science fiction. It's about the long-term survival and flourishing of humanity and our descendants. It's about spreading throughout the galaxy, establishing countless homes on countless worlds, ensuring that no single catastrophe can end our story. It's about exploring the cosmic environment we inhabit, seeking out other intelligences if they exist, and participating in whatever larger galactic community might be out there. The journey from here to there will be long and difficult. It will require breakthroughs in physics that we can't yet imagine. It will require technologies that don't exist and might seem like magic by today's standards. It will require sustained commitment across generations, societies willing to invest in projects whose payoffs won't come for centuries. But humanity has made such journeys before. We've gone from caves to cities, from stone tools to spacecraft, from huddling around fires to manipulating the fundamental forces of nature. Each step seemed impossible until we achieved it. Flight was impossible until it wasn't. Splitting the atom was impossible until it wasn't. Landing on the moon was impossible until it wasn't. Breaking the light-speed barrier might turn out to be impossible, genuinely and permanently impossible, in ways that flying or nuclear fission never were. But it might not. And the only way to find out is to keep trying, keep learning, keep pushing against the boundaries of what we know and what we can do. As you drift off to sleep tonight, let your mind wander among the stars. Imagine a future where humanity has spread throughout the galaxy, where the journey from Earth to distant worlds takes hours instead of centuries, where the stars that seem so impossibly far away become neighbors. Imagine stepping onto a spacecraft, engaging a drive that warps spacetime itself, and arriving at a world orbiting a star so distant that its light took thousands of years to reach Earth. Imagine looking up at an alien sky, perhaps with two suns or none, perhaps with unfamiliar constellations, and knowing that human ingenuity and persistence brought you across the unimaginable gulf of interstellar space. That future might come, or it might not. But the dream is worth pursuing, the questions are worth asking, and the journey is worth taking wherever it might lead. And with that thought, let yourself relax completely. Let the day's concerns fade away and drift gently into sleep, secure in the knowledge that somewhere, someone is working on turning these impossible dreams into reality. If you enjoyed this journey through the physics and possibilities of faster-than-light travel, please consider liking this video and subscribing to the Science Pillow. Your support helps us continue creating content that merges scientific curiosity with relaxation, making complex topics accessible while helping you unwind and drift off to sleep. New videos exploring the wonders of science, nature, and the cosmos are released regularly, each one designed to educate your mind while calming your body. Thank you for joining us tonight, and we'll see you next time as we explore another fascinating corner of our remarkable universe. Sleep well and dream of the stars.